Simulation for Electrification session. My name is Letizia Ferrara and I'm Senior Application Engineer at Altair. Altair solutions cover a wide range of topics around electrification, including batteries, power electronics, PCB, and motors. So in the next 50 minutes, during this session, we will show you how to unify motor and control simulation for better system performance. I will start to talk on e-motor design process and how to generate the motor model with FluxMotor. Then Nikos will show you how to couple the motor model and the power electronics with PSIM. So lastly, Marek will delve into printed circuit board level analysis with PollEx. Starting with e-motor design process, our solution can be divided into three main poles: the concept design, that required an extensive and rapid design exploration, ranking for feasibility study during the concept phase. This can be made with FluxMotor. Detailed design with advanced solvers and multiphysics. I'm talking about finite element solution for electromagnetic, CFD, and so thermal management. To conclude with stress analysis and NVH simulation. So we have specific tool for each of these fields, but we also have a single tool named SimLab that includes all of these solvers and offers to the user a simple multiphysics workflow. Both of the design levels offers the possibility to link the motor with the system modeling to include inverter strategy, so the control and global loads to the machine. We have several workflows and tools to allow automation and optimization in this field, but today I want to present you FluxMotor that allow us to face the first stage of the process, the concept design, considering the full drive. This full drive approach gives us different advantages. We can use advanced inverter modeling methods in PSIM to take into account the efficiency and thermal of such power electronics correctly. We can compute the harmonic content of the current flowing in the motor winding, so we can consider it to properly compute the power balance of the complete drive, considering the inverter losses and the losses in the motor due to the harmonics content. And we can also have the impact of the control strategy. So we can obtain at the end a more accurate efficiency of the powertrain. E-motor design is not a simple task, so we normally have to meet multiple goals and respect multiple constraints in an early stage of the design process. We deal with multiphysics constraints such as noise, temperature, and of course electromagnetic efficiency. And we normally have to find the best compromise between cost performance and weight, manage thermal and noise issues, and get high power and torque density, increasing the motor efficiency along the duty cycle. So FluxMotor is the tool that allows us an efficient machine pre-design and quick performance evaluation. Let's see the result. So with the FluxMotor, we are able to obtain a good maturity of design with a simple setup. Since it's a multiphysics tool, we can perform performance maps, thermal and NVH simulation, and we can consider the skew and compute the demagnetization. Within Flux then, that is the finite element electromagnetic Altair tool, we are able to go one step further from FluxMotor with more capabilities and more freedom on the simulation we want to perform. This includes many types of analysis, as we can see in particular advanced types of results, such as 3D effects. So the Flux model can be easily exported from FluxMotor, and this can help us a lot. FluxMotor is an e-motor concept design tool, as we say, that allows quick and easy multiphysics simulation of an electrical machine. It combines best practices of e-motor design in an intuitive environment and is optimization ready thanks to the quick and accurate computation. We can find the best solution in a short time. Altair FluxMotor is mainly for radial flux machine design, but is constantly evolving. In fact, the developers team is working on axial flux machine, for example, that will be available soon. So today you can find synchronous machine with permanent magnets, inner and outer rotor, reluctant synchronous machine, induction machine with squirrel cage, inner and outer rotor, and the possibility to add skewing to slots, magnets, and bars. So more machine types to come soon. So let's start with the demo. And before open the FluxMotor supervisor, let's see the motor that we are going to manage and export. This motor is already available in the FluxMotor standard catalog. And for time reason, we will keep the design. So it's an EPM three-phase machine with an external diameter equal to 198 millimeters, 150 millimeters of length, and 48 slots, 8 poles. Very similar to the Nissan Leaf motor, especially to the model EHAM61. So the power is 96 kilowatts at 4 kilo RPM. The max line current RMS is 300 amperes, and the max line voltage are 265 volts. Let me show flux motor. This is the supervisor that we have, and we can find different sections. The materials that contain all the predefined materials that we have. You can create new materials. The part library that contains all the part of the motor, rotor, and stator parts already parameterized that we can use to create our motor, and the motor catalog that I'm going to open. So this is the motor catalog section. Here we have some reference catalog divided into different topologies. We have synchronous machine, so permanent magnet, and the reluctance machine with inner and outer rotor. We have also induction machine here, and we can create our own catalog. To see all the motors that we already have in the reference catalogs, we can just click on some catalogs and see the content. In our case, we want to go in depth in the automotive transport catalog to check the Nissan Leaf motor. And you can see when I click on the motor, we can have the general data here and the performance. This is because the motor is already performed. So we can just click on three models, for example, add to the comparator and compare them. And here we can compare the overall dimension, for example, the operating condition, the performance, such as the mechanical power, the power factor, the ripple, the mechanical torque, and the machine characteristics. For example, we have the power density and the constant of the machine. To conclude with the masses and inertia. Also with the constant of the machine, we can start to consider the motor in our drive, but today I want to show you how to create the motor model. So we can create a new catalog. Clicking on plus, we have to put a name. It's just an example. The family is synchronous. We want to analyze a permanent magnet machine in a rotor three-phase. So I can just click on OK, and I can see here my catalog. Now I want to start from an existing motor, the Nissan Leaf one. I have to go to the catalog and click on the motor and click on Edit. Change the name and choose the catalog. So it's going to open the new environment, which is called the motor factory. And here we can do the design of the motor. So starting from the design, the workflow is always from the left to the right, and you can find the input then at the right side. But if we continue with the test section, we can find some tests already predefined and ready to be used. And here we have, for example, a datasheet test already performed. We have at the at the right side the input, in the middle the view, and to the left we have a summary. So with inputs, settings, and the main results, such as curves and so on. So here we can see, for example, the base speed point. We have 4,179 RPM, and here the mechanical torque. So we can see all the characteristics here, all the data and graphs. But now, today we want to test our model. Before it, let me go in depth in the design section. We have the possibility to change the topology, such as the number of slots and poles, the overall dimension, the high gap length. We can set fins, radial or parallel fins. We can set the water jacket, and we can define the shot and the bearing. If you click on the bearing here with bearing, the internal cooling section will be available then to define the internal transfer, thermal transfer of the machine. We can go to the rotor tab. Here we can change the magnet shape. We have this magnet shape that was already available in the catalog. And here we can find the input parameters that we have. Once you click on one parameters, the description in the view appears. And you can just edit the value and change it. For example, we want to change the dimension, so the length of the exterior magnets to 3. We can click on apply inputs and continue. Here FluxMotor let me that if I continue with the changing, the results will be deleted, but no problem. We can just, if you are interested to save your design, you can just save here, save the motor changes here before editing it. Okay, so here we have some output parameters that will be changed depending on the first one. We can also add skew to the rotor, continue skew. We can check the polarization that is already set. Then we can go to the stator part. We have here the design. We can change the lamination type, and we can add also the skew. Also in the slot part here can be also changed, just clicking on this button that allows you to go to the material to the library of the parts, and clicking on the family, you can see different parts with some predefined parameters. So we can go to the winding. Here we can wind it, evaluate the architecture of the winding, do MMF analysis, and to see the quality criteria, and to evaluate the relevance of the winding architecture. Four winding modes are available. The first one is completely automatic. And then we can define the winding in different ways. Each time you go to the right, some parameters appears to hand with the expert mode, where the user can define the winding coil per coil, like this. We have the tab here, and we can put all the coil. We can define them. Then we have the possibility to use hairpin, and we can define the coil. So we have to define the wear topology, the slot filling, and we also have the possibility to consider different grouping methods. So then we can set the cooling, the external cooling and the internal cooling, because as I told before, FluxMotor is able to perform thermal analysis with an equivalent network. And we can define all the materials of the machine here, also for the cooling system. So if we go to the test tab, we saw the data sheet, and The data sheet is normally the first test that we do, since the aim of this test is characterize the behavior of the machine when operating at the working point that is located at the base pin point here that you can see of the torque speed curve. And it is defined by considering the maximum allowed line voltage and the maximum allowed line current. So in our case, we want to we want to perform a model motor maps here. That is the test that allow us to give to the maps in JDQ plane for characterizing the three-phase synchronous machine with permanent magnets in this case. So these maps allow predicting the behavior of the electrical rotating machine at a system level. So what we want to do is to set the inputs that we need here. So the operating quadrant is by default the second, because we want to consider the motor function, the motor operating system. Then we have to set the maximum current density, that in our case is the maximum line current in RMS, and we have to set 300. Here we have the maximum speed, could be 10,000 RPM. We can also consider the rotor position dependency. So if you click on yes, the time will increase, and also for sure the data that we will export will increase of size. And then we can choose the number of computation for JDJQ in the quadrants, and also the number of computation for speed. So to be more accurate, we could increase, for example, the number of the computation to 15 for the JDJQ computation and 20 for the computation speed. So we can consider also the skew model, and we can choose the number of layers. 3 is fast. 5-layer normally is better. And yes, we can click on apply inputs and click on start test. So in our case, just to save time, I already prepared a model. So we can take it from the short video and edit. In the meantime, I recommended you to go to the preferences to allow multi-session here, and also to set the flux distribution mode, because it can run in parallel. So going to the test, we can see that we already have performance test here. Clicking on it, we can see the inputs here that we use, the settings, and the winding and magnets characteristics. Then in the maps section, we can find the D and Q axis flux linkage map. Clicking on one of them, you can focus on just one map here. We can proceed with the dynamic, cross-dynamic, and static inductance map. In fact, we can see them here. Then the electromagnetic torque and losses. Iron losses, rotor iron losses, and joule losses here, and the total losses. In this case, the power electronic is not available since I didn't use the electronics. I didn't add the electronics stuff to perform my case, but you can do it, and you can also set the temperature, the relative temperature for the machine, and also the mechanical losses. To conclude with the curves of magnet, the axis, flux linkage versus current, and the mechanical losses here that are not available since I didn't fill the data here, the input data here. So great, we have other tests already available. So the open circuit, the coping torque that require just that doesn't require any inputs. The back MF that require just the speed of the machine. We can also analyze the working point, the machine at the working point with sine wave or square wave supply. And we can also perform performance mapping and better understand the mechanics aspects of our machine, going to the radiated sound. In our case, we want to export the motor model. So we can go here in the export tab, clicking on the test. We can import the test that we already did. Choosing it, we can see that the parameters, the input parameters here can change depending on the test that we did here. And to conclude the export, we have just to give to FluxMotor some information. So, for example, the destination their name, the format that we want to export. In this case, we need the MAT file because the model will be used in PSIM. But we also have the possibility to export FMU for Activate, that is another tool, another Altair tool, and generic FMU and the destination folder. Then we can just click on export model, and great. What I can find then in the output folder is the matte angle folder with the matte file here that we can use in PSIM, and Nikos will show you how to use it, and all the data that FluxMotor computed here. So we have a lot of text files that you can open and discover. So the data are the same that we have in the test and that we already seen. Other possibilities here are the hyperstudy link, so we can directly export the model to perform some optimization. Hyperstudy is our optimization tool. We can export the model for Flux 2D, Flux 3D to considering the skew in a 2.5 domain, and also we can export the Flux 3D model. But another thing that is quite important and useful is the report. We can create easily some report of the machine with that contain the design, the test that we performed, for example, and all the material, and share it with the colleagues or the customer. So what Nikos will show us is how to considering the PWM, so the harmonic content of the inverter. Let me show you. We can continue with the detailed analysis with the flux, since it is very simple to export the model. And we can link the currents from PSIM with flux. So we can enter the currents waveforms into flux, into the flux model, and compute the thermal aspects, so the temperature in the machine, and also the forces acting on the stator teeth with SimLab, for example. So it is quite simple in this case to consider different harmonic content at a different switching frequency. We have some example here, compare it with the average model. And also here we have the FFT. So considering them, we can compute the ripple, the torque with the flux. We can check if we have some parasitic forces, and we can recompute the vibration and noise stuff to see if we have some modification in the behavior of the machine. But we can also, oh yes, in fact, some harmonics can show up within a certain frequency range. As you can see, we don't have it in the average behavior, but we have it at 2 kilohertz and 5.5, 7.5 kilohertz, not at 20 kilohertz. Another thing, we can also check the losses. So the losses can change in the machine. And especially, we can see here for the magnets, we have a quite huge amount of losses at 7.5 kilohertz. This is not happen at 20 kilohertz. This means that if we compare the final temperature in at the average behavior and considering the switching frequency at 7.5 kilohertz and 20 kilohertz, we can see that the rotor has higher temperature than the other two cases. So this is my last slide. So thank you for your attention, and let me leave the floor at Nikos. Thank you so much.
Hi everyone, thanks for being here, and of course, thank you Letizia for introducing us into Flux. My name is Nikos Dimitrakopoulos. I work as an application engineer within Altair's office in Athens, Greece, and my main area of expertise revolves around power electronics. So naturally, today I'm going to give you an overview on PSIM, Altair's solution for power converter design. We will grab some slides first, and then we can take a look at the software itself. So, without any further ado, let us discuss how PSIM can simplify your power electronic design efforts and help you delve into some useful insights for your motor drive systems. Uh, let's talk some history first. PSIM has been a leading simulation tool for both power supplies and motor drives for almost 30 years now. It kind of bridged the gap for power electronic simulations around the same period that power sheets became commercially viable. And it occupies this nice little space between circuit simulator software such as SPICE and system/control simulators such as Simulink and Altair Zone to Inactivate. And of course, all these years, it's widely known for its simulation speed and robustness, and the fact that it can run dependable simulations no matter the complexity of the power state system. And let's see what makes PSIM so special. Of course, a lot of has to do with the PSIM engine. So when you open PSIM, you will be faced with just two solver options, the fixed step solver and the variable step solver. And you are just 3 clicks away to get your simulation running. Both those solvers accommodate what we call time correction for the switching. So this essentially means that PSIM is able to understand when the switching happens and accommodate for the correct T on and T off times for the switches, even with coarser time steps used for the simulation. And of course, PSIM is specifically designed to deal with the large derivatives that comes with high power, high frequency switching. So this is a major problem, both in reality and in simulation when it comes to power electronics. And it's the major cause for many converger issues for solvers such as SPICE that aren't specifically designed to deal with those large derivatives. Letizia presented us with Flux, so I want to focus today's presentation on motor drives. But please bear with me for a second. I just want to show a simple example of a power supply and how fast it can be solved within PSIM. So in this case, we have a phase-shifted full bridge DC-DC power supply. This can be used for a battery charger application. And this simulation incorporates 6 active switches and 2 transformers with analog control. And it is able to solve to steady state in 2.5 seconds with a 200 kilohertz frequency. So I also want to showcase that you are not limited to analog control. You can digitize your control loops. There are multiple blocks for zero order holds and sampling and zeta transformation blocks and unity lace and all that stuff. And what is more, you can translate your digital control into actual usable code with the auto code generation tool in PSIM, but this happens only for a selected list from Texas Instruments MCUs. Um, Okay, so now let's dive into the motor drive simulations. And of course, with motor drives, you can do all that. Plus, you have a list of 33 motor models to choose from with different levels of fidelity. PMSM motors, induction machines, reluctance, you name it. And of course, PSIM is equipped with a lot of blocks to help you build your field oriented control easily. So there are Parks and Clark's transformation blocks, um, uh, modulation blocks such as space vector modulation, DPWM min and max to even compare what modulation technique to choose for your motor drive. And of course, you can implement more advanced stuff such as maximum torque per ampere control or field weakening. Um, and another nice feature that also applies to power supplies, it's the semi-automatic uh, PI gains calculation with the AC sweep and smart control. So let's discuss this a little bit. Smart control is an Altair partner tool that help you define the controller gains without trial and error. And the process is very simple. So you first need to drive the frequency response of your power states. So essentially the body plot of your system. And the nice thing about PSIM is that it views this workflow in an entirely different way. So you just need three things to do that. Um, you need the AC sweep block. You need an input excitation, a perturbation. So let's say in this case we want to control IQ here, and we want to build a PI controller around IQ. So we add to IQ a perturbation, oscillatory excitation, and then we measure the effect of this excitation to the system. So in PSIM, this part, so the whole power states and the control states that is not involved with IQ, can be considered as a black box. It doesn't matter what's inside. It can be a more complex system. It can be a power supply. It doesn't matter. By following this procedure, we select in this ACSU block the starting and ending frequency and starting and ending amplitude of this excitation source, and we run multiple time domain simulation. So those are actual switching simulations, not average models, and we get the system response for a specific range of frequencies. And then we can import this frequency response of the power states into smart control to graphically select the operating point of the system to have the controlled parameter to have the response we want in an essence. So let's maybe jump into PSIM quickly to see how this can be done. Okay, so I have the same open loop example for this PMSM motor drive. This is the simplest example possible for field oriented control. We have the simulation control here with the two solver options I mentioned. We have a switching frequency of 10 kilohertz, but because we have time correction, we can get away with two microseconds time step instead of 1 microsecond. Um, as far as the switch model is concerned, we have an inverter here with IGBTs. I have selected the ideal IGBT model. We can also offer higher fidelity models that include the parasitic capacitances and the details on the reverse diode path. And of course, thermal models that can be driven from the datasheet of the switch to help you calculate the losses based on lookup tables that comes from the datasets. So let me quickly connect this switch again. Okay, and for the PMSM motor, we are currently using the simplest one. it's just a linear model. We can also have non-LDR models and models that come from Flux, and we can discuss this in a bit. Of course, we also have sensing devices to build the control around, some current sensors. Uh, we have introduced the DQ transformation blocks to go from the ABC system to the DQ system. And for the modulation, we have selected space vector modulation in this one. And these are the actual gate signals that drive the switches. So, as you can see, I have introduced the AC sweep block here. This is the perturbation. This is actually summing, it's adding this sinusoidal source to the reference of IQ, and we're measuring the results to the feedback of the IQ. So, for this frequency response, I'm starting at 10 hertz to 3K, and we can run that. It will run 51 simulations. So this can take a little bit. So let me cheat, cheat, cheat a little, and let's just open some pre-saved results I have. So I opened Smart Control. You can open it from inside PSIM. Let me grab my results. This is a current mode to control. So the results I have set for the system are here. My switching frequency is 10 kilohertz. Click OK, select the current sensor. In this case, we just have a unit gain sensor. We will beat a PI controller. Let's choose some logical values for the compensation of the controller. There are multiple tutorial videos on how to choose those parameters. And the fun part starts here. So Smart Control offers you a nice graphical way of selecting the operating point for your converter. In this case, we want to control the IQ, and we are greeted with a map that has the cross frequency in the x-axis and phase margin in the y-axis. And we can select an operating point based on this crossover frequency and phase margin to get the actual gains for the controller. So let's just pick this as a starting point, and then we're greeted with this menu. So on the bottom right, we see how the actual IQ transient waveform will look like. Oh, and this is the result from the simulation. So it doesn't take that long for the AC sweep. But yeah, this is the IQ transient response, and we can modify the cross frequency and phase margin to make sure to make it fast enough, but also stable, right? We want to hit a good stability point. Let's say somewhere, I don't know, maybe around here would be nice. The purple waveform is the closed loop system, the transient function of the loop control system, and the green is the transfer function of the open loop control system. So by selecting this operating point here, I make sure my system is stable, and I have the K and I gains for my PI controller. And I can then jump into PSIM. Let me grab another schematic where I have already introduced the PI controller. Obviously, there is a PI controller block to use. Here it is. We have input the values here, close to the ones we selected now. We have the feedback for the IQ, and then we can run this. This simple simulation will be very fast, just 4 seconds to hit steady state. And here we see how IQ successfully follows the reference. Okay, now that we have this part done, let's jump back into our presentation to see what is more with the motor drive. So a big update since PSIM acquisition by Altair is the introduction of the FluxMotor model inside PSIM. So Letizia talked about Flux, and essentially you can design your own motor inside Flux or FluxMotor. This will be, of course, a geometry-based model, and you can export that as a lookup table and import that into the dedicated motor FluxMotor model inside PSIM. And then you can integrate PSIM with Flux to build the control around your high fidelity motor model, which is actually the one you also designed in Flux. And there is a lot more in this workflow. So let's say you use this. So this is the dedicated model for the Flux motor. You are also getting the losses of the motor from that. You can get the losses of the inverter with thermal switches. And then if you build the controller around this, you will get, this is a non-linear motor model, so you will get some harmonics for the supply currents. And those harmonics can cause some issues for the motor. So you can grab those waveforms, the current waveforms, you can feed them back into Flux, and you can, for example, inspect how these harmonics can affect the winding and core losses for your motor. And what is more, you can do some extra calculations to calculate the forces acting on the stator teeth. And based on those, you can run vibration and noise analysis to see how the harmonic content can affect the actual noise vibration of the motor. And one of my favorite things is the fact that you can also do simulation automations and data-driven designs by incorporating another Altair tool called Flux. And just to give you an overview of that, because I think it's very important for academic purposes. So you can you can open directly simulation from the design shoot examples from PSIM. Let's say we want a flux motor simulation. So there are pre-built examples for field related control and even more complex stuff such as field weakening here. And then there are multiple parameters here. You can change the model. This can be an IGBT, it can be a MOSFET, a SiC MOSFET. You can change the input voltage. You can change the modulation technique. In this case, it's space vector PWM. It could be DBWM min or max. You can change the field weakening parameters, and you can do that in an automated way with HyperStudy. So you can run a lot of simulation scenarios, hundreds of simulation scenarios to see how all these parameters affect the actual motor drive system. Because we just have one brain, and it's often very difficult to, connect the pieces together. If I change this, what will be the effect? Will my change here for the switch have a big effect on the losses, and will the switching frequency have a bigger effect on the losses, or what can be more easy to do? So by running such simulations with HyperStudy, we can investigate, for example, like this one, cases where we want to select between IGBTs and MOSFET. So obviously here we have the switching frequency in the x-axis and the losses in the y-axis. The blue line is for a Wolfspeed SiC MOSFET, and the red line is for Infineon IGBT module. And we can see why there is a cap when it comes to switching frequency for IGBTs. We can see that the losses of the converter will be highly affected by the switching frequencies, as the switching frequency gets higher in the IGBT case, but not as much for the SiC MOSFETs. And we can also see how the modulation techniques affect the losses. So we can see that when it comes to modulation, the DBWM max method results to lower losses for both the MOSFETs and the IGBTs. And finally, I wanted to discuss, because this is again for academic purposes, the autocode generation capabilities of PSIM. So a very nice example here, and in front of me I have actually some real hardware. So a small PMSM motor and Launchpad Texas Instrument MCU, a development kit actually, with a small motor drive. And here we have a PMSM simulation inside PSIM, but we can see that we have added some target hardware specific blocks. So we have configured the hardware here. This is the F2806 series microprocessor from Texas Instruments. There is a dedicated block for the ADCs to read the feedback for the control. and of course the three-phase PWM for the control. And I was actually working on this to fine-tune the system because okay, I was able to drive some to generate some code out of it, but the motor would be very loud. So I went and changed the gains here a little bit. And now, if I turn on the camera for the actual hardware I have in front of me, so here is the motor. Here is the MCU, the brains of the system, and upon the MCU is a small motor drive development board, again from Texas Instruments. So for this system, I have modeled the motor parameters inside PSIM. This is the motor model I have used. It's just a linear one in this case. I have configured the PI gains, and I'm able to go to simulate, generate code, and then the embedded C code for this type of microcontroller will get automatically generated without me writing any line of code. So I can then import the whole project. So this gets saved, let's say, in this form. So when I click generate, a C code file is created, and I can import this whole project in Code Composer Studio for the Texas Instruments microcontroller. So this is now loaded, and I can click run, and you can see that the motor is spinning. And it's spinning based on the control I simulated in PSIM. And what is more, you can also have interactions with the hardware. So if I jump back to PSIM, I can grab a real-time DSP oscilloscope feature. So this basically emulates the digital oscilloscope of an actual system. And here I'm reading, for example, the voltage, the supply voltage for the motor. I can even change the speed of the motor. So I can put 0.5 here, updated. The speed of the motor changed, but you can see the change in the waveform. So the speed, of course, affects the frequency. And you can see that in here. We can also grab other parameters. So in this one, we have the ID value being 0. And well, it's around 0 most of the time. So yeah, so it's that kind of thing that I wanted to illustrate. So this can be very useful for people that don't want to get into embedded coding specifically. Embedded coding is an art of its own. And if you want to get into a project without having, for a prototype or to inspect some basic parameters for your control, this can help you a lot. So I wish we had more time here to show you more things, but I want to be cognizant of time, and the fact that we have another session with my colleague Marek Jableka. So Marek is our senior technical specialist for electronic system design. I have presented the schematic side of things when it comes to PSIM and motor drive control. And now Marek can inspect the PCB side of things with PollEx. So, Marek, I will leave things to you. Thanks for attending the session. Looking forward to your questions. Bye now.
Thank you, Nico. My name is Marek Jableka. I'm also representing Altair technical team, but my focus is more on the PCB and electronic systems design using the PCB tools. So I would like to give you a short, brief overview of topics connected with the power integrity, which is very important for the power systems, and also some basics of the thermal simulation. The tool that we will use in these investigations is called PollEx. So let us start with the power integrity concept. I like to compare electronics with the water systems because they are close to each other and it's easy to understand the concept. So let's consider a simple water system where we have the ocean of energy, a car battery in the electronics. Then we have a few pipes that connects this ocean of energy with your shower, with your sink, with your valve at your home. And you want to open the water and get this water and just get the shower, brush your teeth, or do something. So what can go wrong in such a system? What can go improper in such a system? Let's consider a high building and not enough pressure in this valve, in these pipes. This way the guy on the ground floor could take a shower easily, but the guy on the last floor with not enough pressure would just see a few drops of water, definitely not taking a shower. So this pressure is not enough on the highest floor. How we would see it in the electronics, if we will analyze a piece of copper in this PCB, you can see this colorful part, which is supplied with the 12-volt connector at the bottom. So we have the voltage of 12 volts in this point, through this piece of copper down to the transistor, to the source of the MOSFET transistor, which tries to draw 100 amps from this metal structure, from this connection. Copper has non-zero resistance. It has some specific resistivity, and because of that, we see a voltage drop across this connection. In this case, it's just a little bit more than 100 millivolts, not a big case. But if we would go further and consider, let's say, such a connection that we have a 100-volt source, we have a piece of copper with 1 ohm, then another piece of copper much narrower with 10 ohms, and we have a MOSFET that tries to draw 10 amps from this branch, and another MOSFET which tries to draw 2 amps from the other branch. So looking at this system, let's calculate the current for each piece of this system. So we have 10 amps at the top branch, 2 amps at the bottom branch, a sum of 12 amps, which we try to draw from the 100-volt system. Now we can, using the resistors, we can recalculate it to the voltage drops, and we can find the node voltages here. So we have 88 volts at this branch, and then for the lower transistor we have 68 volts. On one of the slides the information was that 50 volts is the minimum drain source voltage to operate correctly. So this transistor still is able to draw 2 amps from the source through this distribution network. The upper one, when we calculate the voltage drops, the voltage drop is too big for this transistor to operate. It's even almost 0 volts in this case. From the calculation, it takes minus 12, but it's impossible to take minus 12 volts in here. So why is it happening? Because the voltage drop across this distribution network is too big to get enough high current on the output, so on this specific transistor. So what is the way to fix this power distribution network? PDN, we call it like this in the electronics. The guys that do PCB call it PDN. You can see this term here. The way to fix it is to change the resistance of the interconnects, to fix the power distribution network a little bit, to get enough current flowing and very low voltage drop. If we'll drop down to 1 ohm on this branch, as you can see, the voltage drop is 22 volts. To this worst case point, still enough volts, 78 volts, it's enough to operate properly with this transistor. Next thing, what can go still wrong with this simple system we consider? What is happening if we are using too small cross-section of the pipe and we want to have a very high pressure system? There will be a situation that on a point of time this pipe will explode because of this high pressure and this kind of amount of water we try to transfer through this very narrow pipe. Exactly the same concept can be used in the electronics. The current density, or the current per the cross-section of copper, it acts like a water. If you pump the water into the system through this connector, you have a lot of water per cross-section because there is a pretty narrow piece of copper. Then it flows everywhere on this piece of copper. If there is a kind of short path to the source, or to the sink, to the component that wants to draw a lot of water from the system, you can see if there is a kind of smaller cross section or there is a kind of curve. You can see there's a lot of much more pressure on this side, and then on this source of the transistor or the connection point, we also can see very high current density. If the current density is very high, much higher than the possibilities of the copper, you will heat up the copper and it will one day just melt or be destroyed. And now what we can do to fix these issues, how we can change the resistance of interconnection on the PCB. In most cases, you can play with the width of the PCB trace or PCB plane, so we can increase the width of the copper. This way, you will reduce the resistance of this connection, so automatically the voltage drop as well as the current density will go down. We can in some places, we can reduce the length, so the distance between the source and this transistor or this sink of the energy. So this can also help, but not many cases it is possible. With the height of this copper on the PCB, we can try to play with that, but most cases it's also not possible because there is a technology behind the PCB, and this height is always 35 micrometers or 70 micrometers. The only way to do that, you can see this N in this equation, it means that you can use multiple layers to hold the same current, so parallelize the flow of the current through the PCB structures. And now, how does it look like in PollEx, in the tool? So here we have the same example. So this is a kind of a inverter or kind of a switching system with two big transistors. We have this connector. To make this kind of analysis, to understand and simulate the voltage drop and current density, all that user needs to do is just to find the net, import the design, and then mark the right nets. So there are some ground nets, there are some power nets. It's as easy as just double-clicking on the net and changing the net type to power or the ground. The other thing that user needs to do is to take care about the layer stack. As we told, the cross-section of the copper is the most important part in the power distribution network. So this kind of thickness topics needs to be checked very carefully. If this is right and correct, if the dielectric material is set up correctly, then we can continue the analysis. And the last thing is on the parts. If we have the specific transistor, in our case it would be Q1 or Q2, so we have here some transistors. So we have to take care about the amount of current that these devices needs to draw from the power distribution network, and we can just set up the signal name to the power distribution name, HVDC in this case, 12 volts or PDN or something like this, set up the pin as a power pin, and then we can find out on a specific power rail for this transistor, we can set up the amount of current that this device draws through the pins. In this case, it's 10 amps that this device needs to operate correctly, or it would like to operate with 10 amps on this system. And then we can just perform a power integrity analysis easily, just running the power integrity tool, selecting this node which we want to analyze, the source and the sink, so the device that is collecting the current. I would not overwrite it because I don't want to. I want to save some time, so I will show you how does it look like in the system for the simulation. If we would open this simulation, you will see this board in a simpler way. So just cut it out HVDC part, and you can just run the DC drop analysis like this, and you will see the results of this analysis. So this kind of map which shows you the voltage drop, the current density, as well as the heat density, so the energy generated by the current flowing through the resistive copper. So what else is important on the power distribution networks? Let's go back to the presentation. So what if we have a system that there's a heating element at the one end, there we have a long pipe, and we want to take a shower. We open the valve, and it takes 3, 4, 5 minutes to get a hot water under our shower. What can we do to overcome this kind of issues? To overcome this kind of issues, we have to place a kind of storage of the higher energy very close to the shower. So we can, I don't know, mount a boiler and give a very thin pipe that will just close the loop, and there will be always a delivery of high temperature water close enough to your shower. What does it mean in the electronics domain? We put storages of energy, so the capacitors nearby a specific device. If you will just observe the schematics of the electronic devices and the PCBs, you will see that smaller capacitors are placed close to the transistor to satisfy the need of the energy for the slope, a little bit bigger for whole pulse or for whole big change of the signal, even bigger for the train of pulses, even bigger for all communication, and bigger closer to the source. It's also because the smaller capacitors can be mounted closer, and they are just smaller also not only in the amount of capacitance, but also in the size. When we look on these capacitors also from the perspective of the impedance that they have, so much better, much higher frequencies we can achieve from a small capacitor. So these very sharp slopes are easily supplied with a small capacitor because it's capacitive, its storage characteristics is going up to very high frequencies, like this 100 picofarad is going above 1 gigahertz. Like this, the bigger capacitors, they can store much more energy. They are super tanks, but on the other hand, because of their size, because of their construction, they operate as a capacitor to a very low frequency. That's why you can see on the circuits multiple capacitors with multiple values connected between the connector and the sink, or the place where you need to draw the energy. And here is a simple example. I would not go too deeper into this. You can see the help area of the PollEx, which will guide you through conducting this kind of simulation, or you can also refer to some materials in the network how to do it. Here we can see the outcome of this analysis. You can see that I've mounted 10 microfarad capacitor as a C1, the rest is unmounted. This is the case 1. In other case, I put a small capacitor near to the source and a big capacitor closer to the sink. Then there's more capacitors at the beginning, more big capacitor and more small capacitors. And the last case, I tried to put everywhere this 680 picofarads, very small capacitor. And you can see the first case, red curve, I put it 10 microfarads on the board. The impedance is pretty low, but then for higher frequencies, I can see some troubles, the impedance. So the ability of the power network to deliver the energy is very bad. Then if we increase the capacitor number, the impedance drops at the low frequencies. When we put more small capacitors, we can see the effects in the higher frequencies. So this is the decoupling part of the power integrity analysis, which can be done also in PollEx. And the last thing is the thermal analysis. In most cases, when you want to operate with high currents, you generate a lot of heat in your device, and you need to put some heat sink, you need to solve the problems with the temperature on your board. And this is also possible in PollEx tool. So you can analyze this kind of phenomena also inside the PollEx. So you can just assign the heat for each and every device, and you can just analyze how this system behaves from the temperature perspective. So here we have the same transistor where we just assigned a thermal parameters for this transistor, how much heat in watts this transistor will dissipate to the outer world, and then we can put some constraints on the simulation. So this will tell us what is direction of the board, what are the ambient temperature, what are the types of the dissipation methods here. We can also play with the boundary conditions which are there, and also with the specific components, with the cooling mechanism for a specific components. Having that set, having that prepared, we can run a thermal analysis of the PCB board, just finding out where are the hotspots and how we can overcome the specific hotspot. For instance, for this Q2 transistor, we can consider putting a kind of a heatsink solution which will just conduct the outside with the possibility of 20 watts, kelvins per watt to the 20 Celsius degrees. And we can see easily the impact of this solution on a specific PCB. You can also see that scale has changed a lot. It was 1,000, more than 1,000. So definitely this device is much cooler. So I would urge you, I would invite you to play with the PollEx tool and to fix all the issues you have on your PCB boards. At this point of time, I would just complete the presentation. Thank you for your attention. Thank you for attending all of this session, and really have a lot of fun with the electronics tools from Altair. In the name of the presenters of this session, really thank you for your attendance and thank you for listening. You can find more on altair.com or also on our YouTube channels. Thanks.